Hi everybody, I'm Carlo Cannarozzo, a first-year PhD student at the University of Bologna. And today I'm going to show you my preliminary results about my PhD project on the merger-driven evolution of early-type galaxies. Let's start. We know from the lambda CDM model that the larger dark matter halos are the results of multiple mergers of small halos. In a similar way, we can imagine that the early-type galaxies are the end products of multiple galaxy merging and accretion process. On the left-hand side, we can see a relation between the radius, so the size of an early-type galaxy, and the redshift. Independently from the mass, we can see that the lower the redshift, the larger the size. On the right-hand side, instead, we can see the relation between the stellar velocity dispersion versus the redshift. And we can see that the velocity dispersion tend to increase its value to higher redshift. These two results are two hints of a merger-driven evolution of early-type galaxies. In this work, Hauser et al. In 2010 showed the two-phase formation of an ETGS. And in particular, independently from the mass, we can see that from higher redshift until to redshift around 2, the dominant component of the stellar mass is given by the in situ fraction. That is the fraction of stars formed within a galaxy. While, since from this redshift to nowadays, we can see that the ex situ fraction is the dominant component. A key ingredient for the description of the formation and evolution of a galaxy is the IMF, the initial mass function, that describes the initial distribution of the stellar mass for a given population. There are a lot of IMFs. Here I show you a Chabrier and Salpeter IMF. And some observations, in some observation, we can see that the mass-to-light ratio has a turnover around a value of mass equal to 1 solar masses. I provide you the definition of alpha IMF, or mismatch parameter, or effective IMF. That is, by definition, the true stellar mass, that is the stellar mass formed in a galaxy with respect to what expected by a Salpeter IMF. In this plot, we can see that for the these galaxies are ETGs from Posaki et al. 2015, and we can see that for the higher values of the velocity dispersion, galaxies tend to be described by a Salpeter IMF. Okay, what I want to do is to look at the evolution of the redshift of the star sigma relation. To do that, I selected a sample of 184 galaxies with a stellar mass greater than 10 to the 10.5 solar masses and in a redshift between 0.06 to 2.19. And we can see that also among these galaxies there are some lenses. I would like to make also a comparison with the simulations, and I take from the Illustris project the Illustris one, that is the simulation with the highest resolution, and I selected galaxies with a stellar mass greater than 10 to the 10.5 stellar masses in the 3 snapshots, 0, 1, and 2, and I follow the approach suggested by Blancato et al. 2017 to select the ETGs, in particular with a specific star formation rate lower than 10 to the 11, 10 to the minus 11, sorry. What I want to do is to analyze the evolution of the sigma as a function of the stellar mass and as a function of the redshift. In this formula, mu is the mean value of the sigma. And I used two different approaches. I want to, here I used a Bayesian approach, and in particular, these two different models are characterized by a constant slope for the stellar mass and a slope that evolves with the redshift. And these are the plot of stellar mass and sigma versus sigma. Here, both the curves and dots are colored as a function of the redshift, passing from the red to redshift 2 to violet for redshift 0. This second parameterization is still in progress. So hereafter I consider just this with the constant slope in redshift. To check the reliability of our model, I make a comparison between our feed model with what Auger et al. In 2010 obtained in the SLACS sample. In this these galaxies are selected in a redshift between 0.1 and 0.4, and we can see that if we assume a salpeter IMF, the Auger fits is located between the fit at 0 equals at redshift equals 0 and the redshift equal 1. So there is a good agreement. Now we can see a comparison between simulation and observation. In this case, here there is my sample selected by the illustrious. Red are the ETGs at redshift 2, green at redshift 1, and violet at redshift 0. And we can see that generally the galaxy tend to have a lower value of the velocity dispersion. But, however, what we can see is also that a salpeter IMF is better to describe this kind of galaxies. Sorry. This result is has a good agreement with what found in Xu et al. In 2017. Here the sample is different because the sample here is between 0.1 0.4. But we can see also that in this case, the salpeter IMF for the fits, for the Auger fits, is better than the Chabrier one. And here I show you the observation versus the simulation, and again, we can see that salpeter IMF for this fit can describe better our the simulation. Okay. Coming back to IMF, in merger-driven evolution, we know that galaxies tend to mix their properties. In this case, also the IMF of the two progenitors are mixed. So we performed a set of simulations. Here I show you just the results of two simulations. The simulations are the specialist binary merger with a parabolic orbits. These are the initial conditions. These are two galaxies. The yellow and orange are the stellar particles, while the violet and purple are the dark matter. And these two galaxies have this ratio in mass, 0.5. We have two different cases. One, the two merger after this evolution. In this case, this case is a frontal impact, while this case in the merger is occur after an angular momentum between the two systems. If we assign an IMF of salpeter to the major galaxy and an alpha IMF to the minor galaxies equal to 0.5, what we can obtain is this result. What is this plot? This plot measures the percentage of mass accreted from the minor galaxy onto the major one, and we can see at different radius. And what we can see is that in the case of angular momentum of mergers, the two stellar populations are well mixed with respect to the frontal impact. So in conclusion, I leave here my conclusion. I want to highlight about my future perspective. I want to extend my Bayesian inference analysis about the case of changing slope in Redshift. I want to follow also one by one evolution of early type galaxies, because one problem could be the progenitor bias. And finally, I want to make some comparison between the merger-driven IMF and the observation. Thank you for your attention.
Just some clarification. Is the sigma that you're always referring to the velocity dispersion, is that for the whole galaxy or the center?
It's the center. Yeah.
Why do you think it's declining? Is it mass loss due to
In which sense?
Why are you finding that it's declining with redshift? The red curve is lit up instead of redshift 2, the green one, redshift 1, the vast majority.
Okay, this decline? Yeah.
So is it because lower mass galaxies are joining red sequence, or is it that the earlier galaxies are actually having a decrease, so for example with mass loss and stellar evolution?
Okay.
Or try not to see.
Okay. What we can see in this plot is as a function of the redshift, the velocity dispersion tend to increase to higher redshift. Why we can explain this increasing for higher redshift? When we have a merger or multiple merger events, there are some studies that shown that the velocity dispersion become more flat, and the dispersion and also the value tend to decrease, and it is in accordance. And it is in accordance also with this plot.
Let me try to ask the question again.
Yeah.
You have very few galaxies.
Yeah.
Red dots, and many more dark blue. So the population has tremendously changed. Is it primarily an evolutionary effect? That is, if you look at the same galaxy at earlier times, do you see a decrease in the velocity dispersion? Or is it mainly because new galaxies are joining the sample? And those galaxies started out with lower central velocity. You see that now you understand the question?
Yeah, I know. I understand that. Yes, of course, here there are some galaxies that are the result of the merger of these galaxies. In my future perspectives, I said before that I want to follow the one-by-one evolution to understand also the progenitor bias problem eventually.
So in other words, this is something you haven't answered yet, and they're looking forward to answering it in the future.
Yeah. Yeah. Thank you.